Okay, so in this segment of the video, I'm going to give you one more example, and I want to be honest with you. When I was a student, I used to wonder, okay, so what's the significance of this? Why would anybody want to use the right-hand side to find the left-hand side, right? Because this was much easier. And even if we use a simpler version of that, surface, which is a flat disk, this was still not so simple, right? I mean, this was much easier. Um, because really, I mean, who in the world is going to be interested in finding the flux of the curl of f, right? Some of your questions in your homework would say, find the flux of the curl of f. But I mean, f is given, right? You want to find the flux of f, that makes sense. But who in the world is going to find the flux of the curl of f? I mean, that's almost like forcing you to use Stokes theorem just for the sake of learning this section. Like this is just such a weird, thing. Yes, I understand Stokes' theorem generalizes Green's theorem. Now we can apply this to three-dimensional vector field. But I mean, do you really need this? Because we can directly find this, right? Well, here's an example where sometimes this will be a lot more involved. Okay, so maybe you are interested in some sort of a work, or circulation, or uh, the left-hand side of it. So sometimes it's called the work, sometimes it's called circulation, sometimes it's called the flow. And so you may be interested in what the vector field F does as you go around the circle called C, right? And what happens is if this C, let's say this is a polygon, like maybe it's a hexagon or something, then it turns out that it's a lot more involved to find this side because you'd have to do this for each of these sides and then you have to add them together, right? So in that case, it is a whole lot easier if you do it this way. Now, remember in Green's theorem, a lot of times we had a radius like this. I mean, not radius, the region like this, right? And in order to calculate the left-hand side, which is the FDR side, you have to parameterize each of the four sides, and you have to find FDR for each of these four edges, and then you have to add them. Sometimes it's a lot easier to do the double integral of Quix minus Pei over this rectangular region inside, right? So that's the power of these expressions or these theorems. Uh, this could be complicated. Now, you haven't seen complicated FDR yet, right, for a parameterized surface and for the boundary of the parameterized surface. So this example will give you one of those questions or examples. All right, so in this example, let's say we have an open box, okay, and it's a cube open box upside down. Okay, and why do I want this upside down? Well, because I'm assuming that the open box, the open side is the bottom part, right? So the bottom is open, and so the surface S is the 5 sides of this cube. This is 5 sides of the cube. Okay, so this box has no bottom side. All right, so I hope you can picture this. All right, maybe I can try that to shade this, but I don't think it's going to help. So this side is here, this side is here, this side is here, and the two back sides are here, but the bottom is empty. All right, so just imagine that. It's kind of like having this paraboloid upside down where the boundary is on the bottom. In this case, the boundary is also in the bottom. Okay, so where is the boundary? Well, the boundary curve, I'm going to emphasize this, is this set of 4 line segments, okay? And let me just go ahead and do this counterclockwise. All right, this is my C. All right, so the S is this surface, okay? That's the surface that consists of the 5 sides of the cube. There is no bottom side, and therefore the boundary curve is C, which is this complete loop, consisting of 4 sides. All right, and in fact, I'm going to name these. All right, so let's call this side S1. This is the side 2. This is side 3 and side 4. Okay, so C, the boundary, is C1 union C2 union C3 union C4. And we assume that this is written in this in this order as you go around this loop, right? And this is counterclockwise, which is consistent with outward bound normal vectors. Okay, so that's the way the orientation is given. All right, now if you are going to calculate the left-hand side, uh, left-hand side, yes, I can spell. All right, this that you won't have to do this for. You will have to find this. So you have to find this, a CIFDR for all of these. I is 1, 2, 3, 4. I have to do 4 different integrals, okay? And I will do this because it turns out to be pretty easy. But now you can see why in a situation like this, it may be easier to calculate this side, all right? So this example will show you how to calculate the left-hand side, which is, you would have to do 4 different integrals, but you don't have to, because if you use Stokes' theorem, you can use this side and the technique we showed you earlier here, right? To use the same surface as, not the same surface, different surface S with the same boundary, okay? And then this side will be much easier to calculate. So let's go ahead and try to do that. I am going to calculate the left-hand side, even though it will require 4. And there's a little trick also, okay? So bear with me for just a second. Now, S1, I can parameterize S1 simply as, what is that? T, 0, 0, okay? As T goes from, let's say, for all of these, for all, I'm going to let T go from 0 to 1. So as T goes from 0 to 1, we cover this side S1, right? How about S2? R prime of T is, well, see, on S2, the x coordinate is constantly 1. It's always 1. And then y goes from 0 to 1, right? And then z stays 0. So that is a way to do this. Now, the tricky thing is S3 and S4. The side 3 is going to have negative, right? And it turns out to be, and you can do that, but it's really annoying to have to do the negative of t, because then you take the derivative, it's going to be negative. And so you could do that, but it's going to make it a little more difficult because you would have to have 1 minus t, and then you have to take the dot product. So what I'd like to do is to get the negative of this. We can make the adjustment, the sign adjustment later. Since S3, if you go along this S3, you go from, x is equal to 1 to back to 0, right? So let's consider negative S3. Negative S3 can be parameterized by, what is that? The y is constantly 1, but S is, the x is going, x is t. If you let x equal t, t goes from 0 to 1, you're actually going from here to here, okay? But that's okay. I am just right now considering the negative of S3. So it's a different orientation. We'll fix that later. All right, so this is my parameterization for negative S3, and the same for negative S4. For the fourth one, for the fourth sides, because y goes from 1 to back to 0, I am going to consider negative from 0 to 1. So here, x is 0, y is t, and z is 0, right? So that's what we have. Let's take the derivative of, let's call them R1, R2, R3, R4. So R1, the derivative is 1, 0, 0. R2, the derivative is 0, 1, 0. And for R3, the derivative is 1, 0, 0. And for R4, it is 0, 1, 0. No problem here, right? Okay, so what is F in all of these? On this thing here, okay, F is, now remember what F is? Do I have F? I didn't tell you what F was. Okay, so let's say, yeah, I mean, the problem should define what S is. So S is this, right? And let F be this function, vector field xy, xz, y. Okay, xy, xz, and then y. So if you look at this, now remember F, I need to have this written here. F is xy, xz, y. So if you look at this for each segment, you can rewrite this in terms of t. For this, what is F? you have xy, that this is x, this is y, this is z. So xy is 0, xz is of course 0, y is 0. So there's nothing here. For the second part here, xy happens to be this times this times this, which is t. Xz is 0 because z is 0, and then y is t. Okay. For the third segment, xy is t, xz is 0, y is 1. And then for the last one, xy is 0 because x is 0, and then xz is 0 because both are 0, and y is t. All right, so then you can do f dot r1. That's 0. F dot r2. Oh, sorry, prime. Okay. So you're multiplying, you're taking the dot product of this with that. Okay. So that's going to be, of course, 0. And the middle one also will be 0. The third one, is it also going to be 0? No, it's t. Okay. And then the fourth one, this is 0, right? So that's good. Okay. So what happens here is this. On the left-hand side, it's supposed to be this line integral of f dr, right? Okay. Well, because in all of these cases, t goes from 0 to 1, I can just go ahead and write 0 to 1. And it turns out it's on the side 1, it's 0. Side 2, it's 0. Now, side 3, remember I picked a negative, right? So this will be negative t. And then side 4 is 0. And the t. Okay, that's really all you have to do. So this is negative t squared over 2 going from 0 to 1. It is negative 1/2. And that is the circulation integral or the work integral as the f of vector field f as you go around the 4 sides on the bottom of the cube. Okay, so that's the left-hand side. Now, notice here, in this case, it was easy because my vector field f, I chose an easy one to come up with an easy one, but it still took this long to do this, okay? Because you have to do this for line integral for every single side. You have to parameterize every single side, and these parameterizations may not be so easy. R primes could be difficult, and these could be very hard. And so you can see the pain in trying to find the left-hand side. All right, now the right-hand side. Now remember, S is like this, right? And then the boundary curve is this, okay? But this, let's call this S1, okay? This has the same boundary as, remember, this is a technique I used earlier in the previous section. You can flatten this box, just like you flatten the UPS box when it comes after you take out what's inside. This S2, what's S2? This is the flat square of length 1 or the side 1. Okay, because this has the same curve C. That's the boundary, right? So let's use S2, a flat square with the same boundary. Now I know how to parameterize a flat square, a 1 by 1. It's well, what's the best way to parameterize this flat square, 1 by 1 square? Exactly, u, v, 0. And guess what? You want u to go from 0 to 1 and v to go from 0 to 1. Okay, that completely describes or parameterizes this square sitting flatly on the xy plane. All right, so Ru, of course, is 1, 0, 0. Rv is 0, 1, 0. And Ru cross Rv, not surprisingly, is 0, 0, 1, because the normal components will be looking up like this, right? At every single point, it's the same. Also, f, which was xy, xz, y, right? Well, x is u and y is v. So this is uv. Xz is 0 because z is 0. Y is v, right? And so now we take u dotted with ru cross rv, and the dot product is simply v. All right, so then the right-hand side is going to be the double integral of S. I'm going to go ahead and write this down. I don't know why. It is the curl. Oh, I forgot the curl of F. Huh? I have to find the curl of F. So hold on. I shouldn't be using F here. All right, so this could be a mistake that you may make at the beginning, right? So remember, you don't integrate F, all right? This is what you get, you would do. This is what you would evaluate if you are trying to find the flux of F, but we're not looking at the flux of F. On the right-hand side, it's not the flux of F, but it's the flux of the curl of F. So you have to find the curl of F first, using XYZ preferably, because U and V could be making things complicated. All right, so if you take the flux, the curl of F, so you get 1 minus X, comma. The next one will be the negative of 0 minus X, right? So this will be negative, negative. Well, let's see. That would be the y with respect to x, that's 0. And then xy with respect to 0, that's 0. And then the last one will be z minus x. Okay, so that is your curl of f. And you can rewrite this as what? 1 minus u, 0. Now z is 0, so it's 0 minus x, that's minus u. Okay, and so now we get to do a curl of f dotted ru cross rv. Now remember, ru cross rv is 0, 0, 1. So if you do that, all you do is, all you get is negative u. Maybe I should make a little space here. Let's bring it down, because logically, you have to have this. Oops, sorry. You have to have this expression and this expression in order to calculate that. Okay, so you don't need this anymore. All you need is to take the dot product of curl of f and ru cross rv, and the answer is negative u. Okay, so then you calculate this. That's what you need to calculate, right? And this turns out to be the integral from 0, 1, integral 0, 1, negative u du dv, and this is negative u square over 2 from 0 to 1 dv, and of course that's negative 1. And then the integral from 0 to 1 of dv is also negative 1/2. So you can see you get the same answer, right? But the thing is, I didn't have to integrate 4 different integrals. Here, I did all that in one integral because I found one convenient surface S whose boundary is C, that, the 4 sides of the square, and you use Stokes theorem. So this is, how Stokes theorem is often used. When the boundary consists of a bunch of edges or something, instead of doing several integrals, you can just do all that in one integral using the right-hand side. Okay, so there's Stokes theorem. We have one more theorem to go. But remember, Stokes theorem, the way to remember the Stokes theorem is to draw that picture of that magic carpet, okay? And let green fly. And then you get Stokes theorem. And it still involves work. And, the left-hand side is that work integral around the boundary of a parameterized surface, all right? So once you, see that magic carpet, like I said, you got this whole new dazzling point of view, and you can never go back to where you used to be. And that is the greatness of Stokes theorem. All right, I will see you next time. Until then, I hope you have a great day, a great week. Take care. Bye.